Hello, it's been 3 weeks and I haven't had the time to do anything about this. So, I'm guilty. But I now have the time to continue this, so we are actually going to do it. In this part, we are going to find K1. And what is K1? Well, I'm going to explain in a bit. But first, I'm going to remind you and myself of what we've done. This is what we derived last part, an expression for I prime of A. And what's I prime of A? It's the derivative of I of A. What's I of A? It's this. And why do we have this? Because this is our original integral, and we made I of A as a integral function in terms of A, just to help us solve it. And now we've used Feynman's trick, or differentiation under the integral sign, to find I prime of A. And in addition, I of 1 is the value we want, because when you substitute A equals 1 into here, that gives us our original integral. That is what we've done, and now we are going to continue it. So, our ultimate goal is to find I of 1. How are we going to find I of 1 when we only have I prime of A? The logical thing to do is to integrate it, because if you integrate I prime of A, it's going to get us I of A, isn't it? But we can't just do that, because we want I of 1, not I of A. So we'll have to put some bounds in. If we have bounds beta to alpha, we can make use of the fundamental theorem of calculus, and this will be equal to I of alpha minus I of beta. And since we're looking for I of 1, why don't we set alpha equal to 1? And when we set alpha equal to 1, all we need to do is to make sure I of beta is 0. And we have to find a value for beta that makes this 0. So what makes I of beta 0? Well, if we set if we set A equal to 0, or beta equal to 0, we're going to get this integral, inverse tangent, 0 times x. That's 0. That's 0, because the inverse tangent of 0 is 0. So you're integrating 0 because the denominator just gets rid of by the 0. You're integrating 0 over all space, which is not all space, from 0 to infinity, which is 0. So beta equals 0 is a perfectly reasonable choice, and we are going to use it. So I of 0, and this integral from 0 to 1, and I of 0 is 0, so this is just I of 1. And this is what we are going to solve in the next two parts. Well, this part and the next part. And yeah, let's get started. So, first of all, let me substitute I prime of A into the integral. There we go. Substitute it in. Now let's make use of the linearity of the integral operator and split this up into 3 integrals. There we go, it's split into 3. And now let's factor out these things to the front. Right, this is what we have. And this, remember, is equal to I of 1. And because we now have 3 integrals, I am going to name this integral K1, name this one K2, and name this one K3. So in this part, we are going to evaluate K1. And in the final part, hopefully, part 4, we are going to evaluate K2 and K3. And then we're going to put it all together. So, yeah. Let's find K1 then. So this is K1, and I've renamed A into X, as you can see, just because my brain literally will not function when I try to integrate with respect to A. It just doesn't work for some reason, and I end up writing X all the time, so I'm just going to embrace the X and just live with it. So, standard integration techniques still don't work with this thing, and we're still going to have to, manipulate it, so let's do that. The first thing I'm going to do is to put the natural log up top and write the denominator as 1 minus negative x to the 6 dx. And that's because I want to make use of the sum of a geometric series and the infinite sum from n equals 0 to infinity of r to the n with absolute value r less than 1 is equal to this. And because negative x to the 6, that's always between, well, that always satisfies this because we're between 0 and 1. So we're just going to substitute this in. So that's going to be the integral from 0 to 1 of, let's write that down maybe, x to the 4th natural log x times the sum from n equals 0 to infinity of negative x to the 6th to the n dx. And we're just going to split this up. So that's going to be negative 1 to the n times x to the 6n. And we can manipulate this a bit more because these two, they don't contain n. So from the sum's perspective, they're just constant. So we can just factor those in. So that becomes the integral and then the sum of negative 1 to the n times x to the 6n times x to the 4th, which means we can combine the exponents times natural log x dx. And one last thing we're going to do is to exchange the sum and the integral. I know it might not be proper to do that, but just trust me that it converges, because it does, and we do get the right answer after doing this, so we're just going to not worry about it and do it. Haha. Funny. Okay. We're going to switch the sum and integral, but also this minus 1 to the n, it's independent of x, so we're going to pull that out as well. And we're left with the integral of x to the 6n plus 4 times natural log x dx. And if you've done integration a lot, you'll know this is basically perfect for integration by parts. So we're going to use integration by parts. We're going to set u equals ln x, and that means du is 1 over x dx. And we're going to set dv as, maybe I should write dv over there, down here. dv to be x to the 6n plus 4 dx, and v will be equal to 1 over 6n plus 5 times x to the 6n plus 5 by the power rule. So we're just going to put everything in. So the sum from n equals 0 to infinity minus 1 to the n, that's not changing anytime soon, of u times v, which is, I'm going to write v first, so we have v times u, and then bounds from 0 to 1, and minus the integral v du. So we've got x to the 6n plus 5 divided by 6n plus 5 times du, 1 over x dx. And let's try to find out what this evaluates to. So in the upper bound, if we have 1, we put 1 into ln x, that gives us 0. That just gives us 1 divided by 6n plus 5, whatever. So this bound goes to 0. The upper bound goes to 0. What does the lower bound go to? Well, the lower bound, we'll have to check, because natural log is undefined at 0. It goes down to negative infinity. So that's a bit of a problem. But we're essentially, well, we are evaluating the limit as x goes to 0 of x to the 6n plus 5 divided by 6n plus 5 times the natural log of x. But specifically, x goes to 0 from the positive direction. So let's try to do this. We're going to pull out 6n plus 5 and take the limit as x goes to 0 plus. And we're going to use a little trick here. We are going to write the fraction, well, write the this expression right here into a fraction. We're going to put this into the denominator of the denominator. If I write it out, it will make sense. So natural log of x divided by 1 over x to the 6n plus 5. So I've essentially like reciprocated it twice, and that doesn't change anything. So yeah, and when we plug in x goes to 0 plus, we're going to have that goes down to negative infinity, that goes down to infinity. So we have an infinity over infinity situation, which means we're going to use L'Hopital's rule. So that will be equal to the limit of d dx ln x, which is just 1 over x, divided by d dx, let's see, x to the minus 6n minus 5, just because it's like reciprocated and it's simpler, I guess. So if we do that, we're going to get an extra factor of what, negative 6n plus 5. So negative all of 6n plus 5. So we're going to get negative this squared, and then we're subtracting 1 from the exponent. Yes, that sounds right. And now, let's write this in a better way. So we've got 1 over whatever, because that really doesn't matter in the end. So this limit, and then 1 over x divided by 1 over x to the 6n plus 6 now. And this will be equal to, if we flip everything, x to the 6n plus 6 divided by x, which is x to the 6n plus 5. And of course, the limit to 0 is just 0. So we have now verified that it's 0. And we are now safe to continue if I can delete this stupid thing. There we go. So this entire thing goes to 0. And we will be left with this integral. So let's write this down first. And because we have a minus sign here, I'm just going to add 1 to the exponent here, just so that we don't have the minus sign to worry about. And so what is this integral? Well, it's going to be the integral from 0 to 1 of 6 to the x to the 6n plus 4, because we're dividing by x here. So yeah, and then I'm just going to factor out the 1 over 6n plus 5. Why not? And this should be quite simple using the power rule. We just get x to the 6n plus 5 divided by 6n plus 5, and then integral goes away. Bounds from 0 to 1, bound at 0 vanishes, bound at 1 gives 1 over 6n plus 5 all squared, because x goes to 1, and then, yep. So that gives us 1 over 6n plus 5 all squared. How exciting! And then now, we just have an infinite sum to work with. So this will be the sum from n equals 0 to infinity of negative 1 to the n plus 1 divided by 6n plus 5 squared. And if you have watched maybe previous videos or just integrating, you will know that this is somewhat related to Catalan's constant, because we've got this component here. Well, yeah. Anyways, we are going to get something related to Catalan's constant, but we'll first have to manipulate this a bit more. So, we have got... Sorry, my recording just died there. So, I don't know what happened, but there's going to be like an abrupt cut in the video, but we move on. I don't know what happened. So, anyways, we are going to split this into 2 sums, because we want an odd part and an even part for the exponent, just because this is being annoying flipping signs every single time. So we're going to put the even part first, which means we substitute n with 2n, and therefore we get negative 1 times, not times, to the power of 2n plus 1 divided by 12n plus 5 all squared. And then we add on the even part, substituting n equals 2n plus 1. So we're going to get negative 1 to the 2n plus 2, and divided by, when we put 2n plus 1 in here, we're going to have 12n plus 6. So we're going to have 12n plus 6, but we also have to add this 5, so that becomes a plus 11 squared. And now the numerators become nicer, because this is -1 to an odd power. That's going to be -1. That's -1 to an even power. That's going to be 1. And why not interchange these just so that we get a minus sign in the middle? So we have this sum from n equals 0 to infinity of 1 over 12n plus 11 all squared minus the sum from n equals 0 to infinity 1 over 12n plus 5 all squared. And now we will factor out a 12 from the bottom, just because I want to factor out a 12 from the bottom, so let's do that. And we do that by factorizing a 12 out from the bottom. So because we just can't factor out a 12 on its own, because this is, well, 12 squared technically, we can write this as 12 squared times n plus 11 squared, not 11 over 12. And you can verify that this is correct by multiplying them in, so that's going to get us 12n plus 11 squared if you combine the squares together. I don't know what I'm talking about now. You know what? It's fine. Same thing here. We're going to get minus this, and then 1 over 12 squared, n plus 5 over 12 squared. I don't know why that turned into a 2. That should be a 12. But yeah. So in the end, we get 1 over 144 times the sum n equals 0 to infinity 1 over n plus 11 over 12 squared minus the sum n equals 0 to infinity 1 over n plus 5 over 12 squared. And for those who work with sums or the gamma function a lot, you will recognize that I can write this as something special. The trigamma function, that is a u, I don't know why I wrote a u. The trigamma function, psi 1 of s, can be written as a sum from n equals 0 to infinity of 1 over n plus s squared. That means this is going to be 1 over 144 of psi 1 of 11 over 12 minus psi 1 of 5 over 12. But we are not done yet, because this can be further simplified in terms of Catalan's constant, as I have mentioned before. But I'll do that when I cut the video and then tie it onto the next part. Yeah, so cut. So we have this stupid expression for k1, and that means we have to sort out this middle mess right here. And this middle mess is a difference of trigamma functions. So we aren't actually going to consider this as the difference of trigamma functions. We're going to consider this as the sum of trigamma functions. And how are we going to do that? We are going to make use of the reflection property of the trigamma function. So basically, psi 1 of s can be converted, well, equals something minus psi 1 of 1 minus s. That's something I'm gonna tell you in a bit, because we're gonna evaluate it. But basically, this can be converted into this. Therefore, our psi of 11 over 12 can be converted into negative psi 1 of 1/12. And we can stick this back on. And basically, we just have to consider the sum of the trigamma function at 1/12 and the trigamma function at 5/12. And so, because now we're dealing with the sum of trigamma functions, we are going to make use of something called Gauss's multiplication formula. If you haven't seen it before, because honestly, I haven't seen it before. Why am I saying before so much? Before trying this integral, before solving it. I have not seen it before, but it took some digging, and I found it. So, this is the formula. Quite complicated. 2 pi to the k minus 1 over 2 times k to the 1 minus 2kz over 2 times gamma of kz is equal to the product from n equals 0 to k minus 1 of the gamma function evaluated at z plus n over k. Now, this might look very, very, very complicated, but we're going to work with it. So, this is currently the product of the gamma function. Product of gamma functions, should I say? Plural? I don't know. Anyways. And we're going to leverage this. So, recall that the definition of sine 1 of s is the second derivative with respect to s of the logarithm of the gamma function. And we're literally going to make use of this because this logarithm is going to transform this product into a sum. And so, let's first take the logarithm of both sides. If we take the logarithm of both sides, these products are going to turn into sums as well. So we're going to have the logarithm of 2 pi to the k minus 1 over 2 plus the logarithm of k to the 1 minus 2kz over 2 plus the logarithm of the gamma function kz equals to, if we take the logarithm of this, if we switch the product into a sum and put the logarithm inside, we get the sum from n equals 0 to k minus 1 of the logarithm of the gamma function at z plus n over k. And now, because we want the trigamma function, and as I said, it's the second derivative of the logarithm of the gamma function, why not take the second derivative of this monstrosity? And to do this, we are going to differentiate with respect to z, because z is our, how should I say it? Z is our variable that we want to switch here. And we're just going to do it. So, we're going to take let's take the first derivative. Should we take the first derivative? Nah, let's take the second derivative at once. So, if we take the second derivative at once, these are going to die because they are not in terms of z. They do not depend on z. So, let's look at this. The second derivative with respect to z is going to be psi 1 of kz, but remember the product rule, not the product rule, the chain rule. That means we have to factor out k twice, and we get a factor of k squared. And then, the right-hand side, second derivatives are linear. So, we can just put that inside. And then, this is just the derivative of, well, the second derivative of log gamma, which is the trigamma function, evaluated at z plus n over k. And we don't have to do anything about this because it's addition and it's fine. So, now we have this formula. And we have a sum of trigamma functions. How are we going to work with this? Well, I'm going to rewrite this just so that I have time to process things and I can actually explain what's going on. So we have this thingy, and if you remember, we were trying to look for this value right here, psi 1 of 1/12 plus psi 1 of 5/12. And if you look at this term right here, you'll see that z is just something we can set as whatever we want, but n over k is kind of the incremental value between these two terms. And these two terms have a difference of, I think it's a third. I can't do maths. Wow. Yeah, so 4/12, which is a third. And that means we want the increment to be a third, or because we have n over k here, it's going to be multiples of a third, and that means we want k equals 3, because k is in the denominator, and when n equals 1, it's going to give us a third. When n equals 2, it's going to give us 2/3. It doesn't matter for 2/3, we really want this 1/3 though. So, because it will pass through n equals 1, and when we set k equals 3, it's going to give us the 3 in the denominator we want. So let's go ahead and set k equals 3. What is that going to get us? Well, 9 times the trigamma times 3z is going to be the sum from n equals 0 to 2 of the trigamma function of z plus n thirds. Now, let's explicitly expand this sum. So we have 9 times psi 1, 3z is going to be psi 1 of z plus psi 1 of z plus a third plus psi 1 of z plus 2/3. And remember, we wanted a third difference between these two terms, which is what we got. But now, we want to set z equals a 12th. Why? Because we want a 12th and 5/12ths. And this is going to get us a 12th, this is going to get us 5/12ths. If we set z equals a 12th, we are going to get 9. So we have this thing right now, we have this formula. And remember that we were looking for this value, if I can write please, this value, plus psi 1 of 5/12ths. And if you look at this sum here, this would represent kind of the incremental value between these two. And between these two, 5/12ths minus a 12 is a third. That means we at some point we want this to be a third, basically. So we have this thing, and so we have this formula, and remember that we were trying to look for this sum right here, and if you take a look at within the summation, this kind of represents the increment between your terms, so it represents this difference, and this difference inside the term, well, inside the trigamma function, is going to be 5/12ths minus 1/12, which is 4/12, which is a third, right? So that means at some point we want n over k to be a third. And what better way to do that than to just set k equals 3, because when we set k equals 3, n is going to be 1 at some point in the sum. So if we set k equals 3, we are going to have 9 times trigamma of 3z, which is equal to the sum from n equals 0 to 2 of the trigamma of z plus n over 3. And yeah, that's it. So let's explicitly expand the sum. So we're going to have this equals to psi 1 of z plus 0 over 3, which is just 0, plus psi 1 of n equals 1 this time. So z plus a third plus n equals 2. So 2/3. That should be a psi. There we go. There's a dog barking. Stop. Stop. Thanks. Okay. Never mind, it's not stopping. You know what? I don't care. So, anyways, where was I? So yeah, that was the explicit sum. We kind of just expanded it. And because there's a difference of a third here, this is what's going to get us the sum we want. So that is going to happen when we set z equals a 12th, because a 12th plus a third is 5/12. So let's set z equals a 12th. So 9 psi 1 of 3 times 12th is a fourth, a quarter, psi 1 of 12th, plus psi 1 of 5/12ths, plus psi 1 of a 12th plus 2/3 is a 12th plus 8/12ths, which is 9/12ths, which is 3/4. Quick maths. So this is what we have, and this is very nice because, as I said, this is related to negative psi 1 of 11/12, which will get us what we want from here. But for those of you who've worked with the trigamma function, you know that these two are quite nice, so everything is going to be fine. And I'm just going to rewrite this again, just so that I have time to pre-read my notes and make sure I know what I'm doing. Okay, anyways, I didn't rewrite it, but just gave me time to like read over my notes. But yes, so this is what we have right now. And remember, we wanted negative psi 1 of 11/12, and that's going to stem from this. And how are we going to do that? Well, we're going to make use of the reflection formula, which I think I've mentioned like twice previously, like in this video, but I just haven't explicitly written it out. So I am going to now. So basically, psi 1 of s can be written as pi squared times cosecant squared of pi s minus psi 1 of 1 minus s. And yeah, this is literally what we're going to make use of, and that's what I meant by a thing minus psi 1 of 1 minus s. This is the thing right there. So let's just set s equals a 12th, because why not? So that will become pi 12ths. That will become 11/12. And that's just a 12th. So, yeah, let's just do it. So, this is going to be the slightly annoying bit. And the cosecant function is the reciprocal of the sine function. So that's really 1 over sine squared pi 12ths. And that means it's 1 over 1 minus cosine pi over 6 divided by 2 squared. Because sine squared theta, sorry, not squared, why did I square it? Sine squared theta is 1 minus cosine 2 theta over 2. And this is when theta is pi over 12. So that's what we have. And cosine of pi over 6, we know that. Cosine of pi over 6 is root 3 on 2 divided by 2. So let's reciprocal the entire thing and multiply the top and bottom by 2. So we get rid of the thing. So we have 4 over 2 minus root 3. And let's rationalize it. So 4 over 2 minus root 3 times 2 plus root 3 over 2 plus root 3. The bottom's going to get us 4 minus 3, which is 1. A squared minus b squared, so it's 1. The top is going to get us 8 plus 4 root 3. So great, so this is equal to 8 plus 4 root 3. That was nice. 8 plus 4 root 3. And therefore, sine 1 of 1/12 is pi squared times 8 plus 4 root 3 minus this thing. Yes. And we'll just sub it into this equation. So we will have 9 times psi 1 of a quarter is equal to this thing minus psi 1 of 11/12 plus psi 1 of 5/12 plus psi 1 of 3/4. Yes. And that means if we rearrange this whole thing, moving these two to the left and moving this to the right, we are going to get psi 1 of 11/12 minus psi 1 of 5/12, which is what we want within K1, because that's what we have within K1, equals pi squared 8 plus 4 root 3 plus psi 1 3/4 minus 9 times psi 1 of a quarter. And that means we just have to find these two. And again, these two are quite nice. And we are going to do just that in 30 seconds when I read over my notes again. Right, so essentially we are going to find the values for these just on its own, and we're going to make use of the reflection formula again. So I've written the reflection formula out as this. So pi s minus 1 minus s. If we just rearrange that to the other side, and I'll just sub the values in at this point, we're going to get psi 1 of a quarter plus psi 1 of 3/4. That will be pi squared cosecant squared pi over 4. Right? And sine of pi over 4 is root 2 on 2. Reciprocate that. It's root 2. Yeah, so just root 2 squared is 2 pi squared. I hope that didn't confuse you too much. So what I did was 1 over sine pi over 4. Sine pi over 4 is root 2 on 2, so that's 2 over root 2. That's just root 2 and root 2. So this bit is root 2 squared is 2. And that gives us 2 pi squared. And yeah, so that's the reflection formula doing its job. That's done now. We are going to also find psi 1 of a quarter minus psi 1 of 3/4. My handwriting's getting worse every single second. The way we are going to do this is to use the sum definition of the trigamma function. The sum definition is, well, if we have psi 1 of s, it's going to be the sum from n equals 0 to infinity of 1 over n plus s squared. That means this is the sum from n equals 0 to infinity of 1 over n minus n plus a quarter squared minus the sum from n equals 0 to infinity of 1 over n plus 3/4 squared. Why do I always say minus? Anyways, that's what we have right now. And let's factor out a quarter from the bottom. Might seem weird, but that's what we're going to do. So if we factor out a quarter from the bottom, we are going to get 1/16 because of this squared right here times 4n plus 1 squared. Yeah? And this 1/16 I will be able to pull out front because there is also going to be a 1/16 over here, and it's going to be 4n plus 3 instead. So we have this, and then I have a 16 multiplying the entire thing. And if you just notice that this is 4n plus 1 and this is 4n plus 3, that means these are the terms that are 1 mod 4. These are the terms that are 3 mod 4. So, and the 3 mod 4s are subtracting, so are subtracted off, right, instead of added. So that means it's the alternating sum of the odd numbers. If you want me to make that clear, right, so we are going to have something like, hold up, 1 minus 3 plus 5 minus 7 plus 9. Right, so, ... Reciprocated and squared, but it's just to explain. So, these values are 1 mod 4. That comes from that. These values are 3 mod 4, coming from that. And as you can see, these are all negative, these are all positive. So, that means, yes, we indeed do have the alternating sum of odd numbers, reciprocated and squared. So it's going to be the alternating sum, making sure that the first term is positive by doing -1 to the n, because n equals 0 at the first term, of the odd numbers squared. And lo and behold, what do we have here? That is just Catalan's constant, because it's the definition of Catalan's constant. One of the definitions, but, you know, yes, there we go. That's Catalan's constant, and remember, this stemmed from this. And what happens when we add the two equations together? We get twice the trigamma function at a quarter, being equal to 2 pi squared plus 16g. Dividing both sides by 2 gives us pi squared plus 8g. And there we go. And same thing, well, not same thing, we can literally just sub it in, but why don't we subtract the two equations instead? So this subtract this gives us twice the trigamma of 3/4 will be equal to 2 pi squared minus 16g, which means psi 1 of 3/4 is just pi squared minus 8g. There we go. And going back to the original equation, why don't I just copy this down there? Copy, hello, copy, and, oh, wow, copy and paste, there we go. That means, pen out, this is equal to pi squared times 8 plus 4 root 3 plus psi 1 of 3/4, which is pi squared minus 8g minus 9 times pi squared plus 8g. Yeah, and that is going to be pi squared times 8 plus 4 root 3 plus pi squared minus 8g minus 9 pi squared minus 72g. And we can, let's see, what can we do? This combines into negative 8 pi squared. Cancelling this out with this pi squared multiplies in, and this combines to be negative 80. So that's going to get us 4 root 3 pi squared minus 80g. And remember, this was this. And what was our original equation for K1? 1 over 144 of psi 1 over 12 minus, not psi 1 over 12, minus, psi 1 of 11 over 12 minus psi 1 of 5 over 12. And that means K1 is 1 over 144 times 4 root 3 pi squared minus 80 times Catalan's constant. There we go. That's K1. Sigh of relief there, because I got the right answer and I didn't mess up. So, yeah. But yeah, that's K1. I hope to put out videos more often. Like, I just do. But, yeah. I don't know when the other one's going to come out. Hopefully next week or the week after. But, yeah, that's K1. See you soon.